Most of the proofs in cryptography are done using reductions. Those are similar to NP completeness reductions, but indeed they are more complicated. So the theorem that we are going to prove will be of this type. So we are going to prove some scheme X is secure as long as some, let's say, assumption Y holds. So I will write this simply as if, let's say, Y is secure according to some proper definition, then this implies X is secure. So this is the type of the theorem we are going to prove. The proof methodology will be the same in all reduction proofs. We will prove this using the contrapositive. So what's the contrapositive statement? If X is not secure, this should imply that Y is not secure. So the assumption Y should not hold if X is not secure. And the reasoning, the way we are going to do it is as follows. We will show that if there exists a probabilistic polynomial time adversary, let's say A, who breaks X. Now, what does breaking mean here? Breaking will depend on the security definition we use for X. For example, if you remember the encryption eavesdropper security, it means the adversary wins that game with probability 1/2 plus some non-negligible. Okay? So that's breaking. Breaking depends on the security definition we use. Now, the proof will start by assuming there exists some adversary A. We don't know how A works. We don't know A's code. But we know that A breaks X. If that's the case, then in the proof, we construct another PPT adversary, B, who is going to break Y. So if A breaks X, B is going to break Y. This is what we are going to do. We are going to construct this B. This is very important. We are performing a constructive proof here. Okay? Now, what would this mean? When you think about it, let's say we do the proof here and then we are going to finally conclude. Our conclusion will be something of this form. So one way of thinking it is, we already proved the contrapositive. We know contrapositive is equivalent to the original, so this means we have proved the theorem. The same, let's say equivalent, but alternative way of thinking about it is, since there is no known algorithm, PPT algorithm of course, that breaks Y. There is no known algorithm that's probabilistic polynomial time and it breaks now Y. This will tell us that there can be, again, no PPT algorithm, let's say B, that breaks X. Why? When you think about it, if, or let me change this to B and this to A to be consistent with the above notation, but it wouldn't matter. When you think about it, if there were such an algorithm that breaks X, then through this proof through this reduction, we would immediately have an algorithm that breaks Y. But since no algorithm that breaks Y is known, then it's impossible that there is an algorithm that breaks X.